We're going to continue our discussion of optimization algorithms and look at the EM algorithm. This is an algorithm that comes up specifically in the case where we have hidden or latent variables. So what do I mean by that? We're going to imagine a case where we have some observed variables y. Use a dark border to show that y is observed. We have some parameters theta, and we also have some unobserved variables z. Okay, light border for z and theta because we don't observe those. And then I'm going to use a plate notation here. I equals 1 to n, zi, yi, to say that we have many examples, each of which has a z and a y. This tends to come up in cases that we might call unsupervised learning. So let's give some examples of when we see a setup like this. One example of this is clustering. So clustering in the case where we have a bunch of points like this, maybe a bunch more points like this, and we're trying to divide the points into some clusters. Okay, how can we pose this as a learning problem? Well, we might do something like this. We have an I for each point. So each point in here is one of our i's from 1 to n, and we have some observed data for each one. So for example, in this 2D clustering case, y would be a vector of two values, the horizontal one and the vertical one in this plot. I equals 1 to n for one for different points, and then we have zi, which indicates the cluster membership. So in this case, this would be a value in 1 dot dot k, where k is our number of clusters. So in this case, we have two clusters, 1 and 2. And theta are our parameters indicating, for example, the cluster center. There's a center for the red cluster, there's a center for the blue cluster. So that might be in theta. Let me circle yi with dark to indicate that those are given by the problem. We have z and theta both unobserved, right? We don't know the cluster membership for each point, and we don't know our cluster centers to start. Okay, so that's one example of a problem with latent variables. Here's a second example. By the way, we're gonna derive the EM algorithm for each of these examples independently in a little bit, but I just want to give you a sense of it before we get there. The second case is a case where we have multivariate normal with some missing data. That is, let's say we have 3 sensors, and let's call them y1, y2, and y3. We have multiple readings from these sensors, I equals 1 to n. I'm putting I in the superscript here because I'm already using the subscript. And we're imagining that y is a multivariate normal distribution with some mean and covariance. So if we were to draw the dependent structure, it looks something like this. They're all dependent on one another. And then we have 2 parameters here, mu and sigma, the covariance, and everything is dependent on those. And we're imagining that each time we read from the sensor, some of our sensor readings might be missing. Maybe the sensors are faulty or something. So, for example, the first time we read it, it might be that we get data from these two, but not the third one. In that case, this one would be observed, this one would be observed, and this one would be not observed. Okay, so that's example number 2. Again, I'll give a more thorough definition a little later. Let's give one more example. We're not going to derive updates for this one, but just to give you more of a sense of sort of what we mean when we say hidden variables. So let's imagine we're in a case where we have a bunch of applicants applying for a job, and we're giving each one a score on how strong of an applicant they are. Okay, and we're going to imagine that each applicant has some internal quality that we're trying to evaluate. Of course, we want to hire the strong applicants out of our pool. And each applicant is getting reviewed by a number of reviewers. And so we have scores of I, comma, R. That is the score that applicant I received from reviewer R. And so notice here we actually have 2 plates here. We have I equals 1 to n, the number of applicants, and we have R equals 1 to m, the number of reviewers. And notably, we imagine that each reviewer has some bias, like maybe some reviewers like to give high scores, some reviewers like to give low scores. We see this problem all the time because, you know, if I'm rating someone out of 10, maybe to me, 10 is reserved for only the absolute best applicant, and maybe a normal applicant would be like a 3, and a pretty good applicant would be a 6 or whatever. And maybe to you, you'll give, you know, a normal applicant a 7, and a really, and you know, any applicant that's quite good, that applicant gets a 10 of score. And of course, you wouldn't want to do something just average scores from different reviewers, because maybe you don't have a score from every reviewer for every applicant, and then an applicant could get a good score just by getting a bunch of good reviewers. Okay, so we could solve this again using EM algorithm. Again, here we have applicant is hidden. Our scores are the things we observe, right? Because we see the scores that all the reviewers gave, and then the reviewer bias here, that's also unobserved, of course, and that's kind of taking the place of our parameters. We could imagine we also have some extra parameters indicating priors and whatnot for these variables. Okay, that's just a third example. Hopefully this lets you know what we mean when we say there are hidden variables. And hopefully you get a sense for how this kind of problem comes up very often in practice. Very often we want to reason about some process that's happening that we're not directly observing. How do we handle this hidden variable case? Well, let's look at some options we have, and let me convince you that it's hard, and then I'll tell you about the EM algorithm, which is a way to handle it. Okay, so we looked at kind of 2 different types of solutions to problems in this class. The first is to do just normal inference using Bayes' rule. So that comes up in the case where we have z and y. Of course, if we want to know if you want to do inference over y given z, that's super easy because that's given to us by by the problem. If we want to do, so if y is unobserved, that's easy. If y is observed and z is unobserved, then that brings us back to Bayes' rule. So we had probability of z given y, we've seen this many times, equals probability of y given z, probability of z over probability of y. We can do this inference just using Bayes' rule. So we saw this, for example, if we wanted to figure out if someone was sick or not based on their test result. And then just something to realize is this works as well if we have some theta, some parameters that are observed, that is, they're fixed for the problem, and they can have an influence on both z and y, because then we just get theta at the back of the condition for the whole problem. So theta goes in the back of the condition in all these places. I'm not going to write it in, and everything works. Okay, and so whether you want to think of it as just something inherent to the problem, for example, the false positive and negative of the test, or if you want to imagine that as some random variable that's observed, that is, we've observed the false positive and negative rate of our test. Either way, it doesn't matter. All the math works out the same. Okay, so that's kind of strategy number one we've taken in this class. Strategy number two we've taken is, okay, what if z and y are both observed, and we're trying to reason about some unobserved parameters theta. So this is, for example, in the case where we're doing supervised learning. Z is a bunch of features, and we imagine that they determine our label y. We have a training set where both z and y are observed, and we want to do inference about theta. We've talked about how in most cases we can't just do a posterior distribution for theta. That's usually computationally unfeasible. So instead what we do is we evaluate the log likelihood and take the derivative of that and use, for example, a gradient-based method over theta. Or even better is to we find an analytical solution for theta, which often we can do. Okay, so that's kind of strategy number two we've looked at in this class, where we can't just do inference to find a posterior distribution, but instead we can use an optimization algorithm to find a solution for theta, either analytical or iterative. Hopefully everything I've said is very familiar to you. Okay, let's try applying those tools in this case where we have both hidden variables and unknown parameters. So again, let's draw our case ci, yi. How about let's try doing inference and just calculating posterior distribution? Well, that is to say we want this thing here, probably z comma theta. Those are our two unknown things given y. Let's not even worry about z for a minute. Let's just forget about this. This is p of theta comma y over p of y. Well, what is p of y? That's sum over theta of p of theta y, using theta prime to show that this is a different theta than this one. Okay, and again, generally, for example, if theta is all the possible means for our clustering problem, okay, so then we have to somehow sum over all the possible values of that mean. So if that's continuous, then we're in bad shape. Even if we somehow discretize the means, if we're trying to sum over 10 different clusters, well, we have to sum over all possible combinations of the means, and it's just gonna be totally infeasible. Same thing if we're doing like a logistic regression problem. So we saw this in the case, again, the logistic regression. Sorry, I forgot to draw my arrow here. So even we didn't have any z, or sorry, z was observed. We can't sum over all the possible values we could set the parameters to. Okay, so just again, we can't handle theta usually doing inference over it using, for example, Bayes' rule. That should be no surprise. We already said that we usually have to use log likelihood inference rather than doing a posterior distribution, even without hidden variables. Once we add hidden variables, it's not going to make our lives easier. So much more natural would be to try to find the log likelihood and optimize that. Okay, so let's evaluate the log likelihood. So log likelihood as a function of theta is, well, we have to sum over all of our examples, probability of y n given theta. But notice that here, so again, y is our observed variable. Notice that we don't know what z is, and we haven't included z in here. So we have to include that somehow. Well, the way we have to include it is by marginalizing over it. Okay, right? We have to sum over all the possible values of z, in this case zn, because this is for the nth example. Okay, so in this would be, for example, the possible values of the cluster center. So for example, if this were a clustering problem, zn would be the k clusters that z could be. So this would be a sum of 1 to k. Unfortunately, this is not going to work, because if we try to take the derivative of this thing, I encourage you to give it a try, it's going to turn into a giant mess. Because notice that we have a log outside the sum here. So just think about it for a minute. There's no easy way to, certainly we can't push the log inside the sum. The log is inside this sum because this sum used to be a product, right? This is the log of a product of probabilities. This is an actual sum, not a product. So just take a second, try to take the derivative of this thing. You'll realize that you don't get anywhere. It's really hairy. By the way, you could try just evaluating the likelihood, not the log likelihood. So get rid of the log, then you've got a sum here, but then you've got a product here, and that's going to be a big mess too. Okay, so trying to take the derivative of this thing and trying to set it to 0 certainly isn't going to work. Even trying to use a gradient-based method is going to be really hard. By the way, you could treat the values of z as parameters. So we could do L of theta comma z and do some, for example, gradient descent over both theta and z. That would work in the sense that it would probably eventually converge, but it's going to be super, super slow, because remember, we're used to doing gradient descent over a handful of parameters. So for a clustering problem, maybe that would be, if we had 10 clusters, we'd have 10 or 20 parameters. That's something we can do gradient descent over. We might have 1 million data points. So that is, we're trying to do gradient descent over 20 parameters and 1 million points. That's going to be really, really slow. A much better solution is going to be to use the EM algorithm, which is essentially just to combine these two strategies. We'll use normal probabilistic inference using Bayes' rule to evaluate z, and we're going to use our log likelihood optimization methods to optimize theta. That's the basic idea of the EM algorithm. Next, we're going to derive the algorithm itself. And then after that, we'll show how to apply that to some of those example problems I talked about earlier.